So, good afternoon again. So, before we continue our discussion, so let me just ask you guys one more time. Anyone who has a question or clarification?
None yet, sir.
Okay. So, since no one asked, ako na lang. Now, as you guys can see, this one is a forward bias. But what if we have a reverse bias? So, let's just say that how to flip this one. Where is the rotation? There you go. So never mind the 0.7. Now, what if we have this kind of, our representation, positive to negative and then negative to positive? So as a result, this will become an open circuit. Okay, let's remove that one also. So in other words, we don't have a flow of current. So yes, we still have the value of resistance, but we have zero current, zero power across in everything. Okay, and what are the things that we also need? Yeah, so zero current, still have the value of R total, but zero in everything in here. Okay, and we don't also have a voltage across R1 since this is an open circuit. Okay, so for you to have a voltage across R1, so you must have a flow or a closed circuit from the voltage source to the path itself, and going back to the negative or to the ground of the voltage source. Okay, so yeah, that is the only thing that I would like you guys to know. So if no more question, then let's now proceed to the diode circuit problem in series and parallel circuit. So let's start with series circuit first. Second, let me just close this one. Okay, so in here we have a series connection of a silicon, okay, silicon diode, and then a germanium diode. Okay, so this one is the D1 and then the D2. So we have a total of two diodes in this circuit. So we have a voltage source of 10 volts, and then we have a resistance of 3 kilo ohm. Okay, so in here, in some cases, I don't usually put 0.7 right here, but just to remind everyone, since this is just an example, okay, silicon diode will always consume 0.7 volts. Okay, so it will never change. Okay, that's already a permanent or constant value of a silicon diode. Okay, so there is no way that this will become 0.6, 0.5, or even 0.10. Okay, so it only has one threshold voltage, okay, which is 0.7 volts. So the same with the germanium, it's always 0.3. Okay, there is no way that this will become 0.2, 0.1, or even higher. Okay, so I hope we are clear with this one. So even though there is no label right here, like those 0.7 and 0.3 is not here, you already know that if it's silicon diode, it will always consume 0.7 volt. And then for germanium, it will always consume 0.3 volts. Okay, so in this example, we need to find the voltage, okay, or the voltage on a label VO, okay, and then the total current on a label VO also, and then the total resistance, and then the total power. Okay, so here is the solution, a very real quick solution. So we have here, for you to be able to calculate the VO, okay, so we have this one, Vs minus Vd1 minus Vd2. So as you guys can see, you just simply get, okay, the flow of voltage, okay, before, or what is the reading of the voltage, okay, after passing through this diode right here. So we have a flow of current, of course, which is right here. So it will pass through this 0.7. So just deduct that one. So 10 minus 0.7 will become 9.3 at this point. And then 9.3 minus 0.3, since this will again consume another voltage. So this will become 9 volts. Okay, 9.0, 9 volts. Okay, and then at this point, we have a reading of 9 volts. So that is why we have a 9 volts in here. Okay, and then for the current, so it's 9 divided by 3K. Okay, so it's still V divided by R. So the V right here is not the initial voltage source. So you have to deduct everything first before you can put here the actual value of your V. So, but for the resistance, so there is no problem since it's just 3K, so just put here 3K. So 9 divided by 3K is equal to 3 milliamps. Okay. And then for the R totals, of course, we have 3K ohms. And then for the P total, we have, this is this formula, P is equal to I times P. So 3 milliamps times 10 is 0.03 watts. So this is just the new one on how to get the, the value of VO, okay, on this point after passing through these two diodes. So were you guys able to follow that one? Okay. So one more thing, because some of my students before got confused. So when we say, nandito na nga pala. So when we see, the reading, okay, on at this point, let's say this is label or node node A. Okay. So this one is not the same as having a reading of voltage across this path. Okay, kasi yung akala ng iba, it's like the reading on this point. Okay, but it's not something like that. Okay, so in here, what is the reading of your voltage after passing through this one? So since the label is right here, then we have to compute whatever voltage drop we have in here. Okay, but if we have the VO in here, okay, then we have to include this one also. So VO minus VD1, okay, the voltage of this diode, and then minus VD2, and then minus the voltage drop on this R1. Okay, so that is now the value of your VO, okay, voltage on this or at this node. Okay, so I hope we're clear with that one. So moving on, we have here a parallel connection in which we have to solve or we have to find the same unknowns. We have the VO, total current, total resistance, and then power across R1. So in here, let's apply the the basic of electricity. So let me just get this one. Okay, so anyone who would like to answer, what is the value of our VS after passing through this circuit right here? Anyone? So let me give you guys an option. So letter A, the value of VO, okay, the voltage after passing through the germanium and then silicon will be equal to 6 volts. For letter B, we have 6.7 volts, and then letter C, VO is equal to 6.3 volts. So pick one only. So what are your answers? So you can comment that one in our chat box. And then let's see how many of you will get the correct answer. So coming from Mr. Tanikala, he said that it's 6.7. What about the others? Do you guys have the same answer or same this one, same assumption? So what about you, Mr. Enrique? 6. Okay. What about you, Miss Jennifer Ann? Hmm. So I think she's not around. Well, anyway, what about you, Miss Grace? So 6.7. So we have 6 and then 3, 6.7. Okay, so the correct answer is letter B. Yes, so maybe some of you were able to get the correct answer. So the correct answer is 6.7. So again, from, let's go back with the basics of electricity. So again, the electricity has this kind of thing in him, wherein if he thinks that there is a lower resistance in this path, that is where he will always go, or there is a lower voltage drop. Okay, that's basically the idea of a flow of current. So in here it will only flow in one diode. Okay, so the lesser the voltage drop, so that is where it will go. So in here we have a voltage drop of 0.3. So we have here 6.7 volts at this point. Okay, so here's the effect of a short circuit. Okay, like once we pass through all of the voltage in here, everything. So this is like, will be gone. Okay, so this will like jump to right here. Okay, or just basically remove that one. Okay, so here's the solution for the number 3. So VO is of course 6.7 volts, and then I is equal to V divided by R. So 6.7 divided by 5K, because that is the value of our resistance. And then we will get 1.34 milliamps. And then of course our total is 5K. And then for the power across R1, so it's IR1 times VR1. So IR1 is 1.34 milliamps multiplied to, oops, why do we have two 1.34 here? I squared PIV 1.34 times 5. Hmm. Okay, wait a second. Let me just double check this one. 1.34 times 5,000. Oh, I see. Okay, so I just remember that when it comes to power, okay, so we have to pass through everything. So that is why we have two 1.34 right here. So we have a current of 1.34 in this, and then we have a current of 1.34 in here also. But how come that they are the same? If we only have one, the result is 6.7. Why is it milliwatts? Okay, let me just check. 34. Square. Yeah, we have 8.978 milliwatts. Okay, so for now, this will be my assignment. So my bad, I wasn't able to notice wherein why we have two 1.34, like we have the current in here, and then we have another current in here, VR1. So if it's IR1, then it should be 1 only. And then voltage across R1. Ah, this one is correct. Okay, so this one is correct. So my bad. So the one that we are getting here is the VR1, which is the voltage across R1. And then how to get again the voltage across R1? So it's I times R. Okay, so that is why we have 1.34 milliamps right here, and then the value of R1. So 1.34 milliamps times 5K is equal to 6 point something. And then since we are getting the power, so we have to use that one. Okay, so the value of VR1 times IR1 again. So that is why we have 8.978 milliwatts. Okay, so I thought this was a mistake, but it's not. Okay, so this one is the VR1 itself, and this one is just the IR1. So again, I'll give you guys maybe 20 to 40 seconds to analyze everything. And then just give me thumbs up once everything is correct. Or if you don't have a question or a problem anymore. Sobrang tahimik ah. Okay, so let me ask a random person. So Miss Sophia. Miss Sophia Nicole. So guess she's not around. Maybe she's doing something. What about you, Mr. Isel de la Cruz? Wala din. So hula ko parang dalawa or tatlo lang yung meron. So for sure, Miss Macabio is right here. Mr. Macabio. Mr. Macabio?
Yes, sir.
Okay. So any questions so far?
Pag parallel ba, sir, will it always go through diode 1? Kasi you said how to solve, di ba? Ano yung lalabas na voltage na VO if yung circuit is parallel like that? Yung parang ganito, sir. Lagi bang dadaan sa
Just a lesser
D1?
voltage. No. So of course, you have to check if whichever is the lower voltage drop and then a lesser resistance. Okay.
Okay. Okay, sir.
All right. So in other words, the other one will be like ignored. So this will become an open circuit. Okay. Okay. So no question for Mr. Isel and then Miss Nicole. Okay, so if you guys don't have a question anymore, then let's now proceed to the example number 4. So we have a series connection, but in here we have a twist, like we have to pass across this R1 first before the diode itself. So solve for VO, total current, and then total resistance, and then the power across V1. Okay, so let's have the solution. So in here, it's the same. All you need to do is remove, or deduct the voltage drop. Okay, and we have this equation right here, Vs, okay, which is this one, minus VR1, which is the voltage drop across R1, and then minus VD1, which is the voltage threshold of your silicon. So for the Vs, we have 10, and then VR1 is, of course, the I times R1, okay, wherein our I is, or you must solve for the I first. So I is equal to V divided by R. So voltage is equal to 9.3 volts. Okay, so just solve that one by, you know, solving this one first, or solving the entire circuit first. Okay, so we have 9.3 divided by 3k plus 4k, and then we will get 1.33 milliamps. Okay, and then in here we can now substitute the value of 1.33 and then add 3k, and then we will get 5.31 volts up to this point. Okay, so you can also use KVL, okay, using this kind of expression. So I will leave on how to do that one because I've already taught this one on electrical circuits. So in here we just have a clockwise, okay, and then just label everything positive, negative, positive, negative, positive, negative, and then you will get this kind of equation, and then just simplify it, and then you will get the same result, which is 1.33 milliampere. Okay, and then for the R total, of course, it's 7k since they are in series. Just add them, and for the power across D1, so just use this formula I times VD1. So 1.33 milliamps multiplied to the voltage of the D1, which is 0.7, and then you will get 0.0931 milliwatts. Okay. So I think the only hard part is these two. But yeah, I'll give you guys 30 seconds to 1 minute to double check everything. And then if ever you have a clarification, so just let me know. Okay, so two of you were already able to get this one. Okay, 3. So I hope you guys have already realized that the voltage on our diode is like it's like another voltage, wherein in here we have the negative positive, and then this one is positive negative, so different polarity, and then the higher the voltage, that is the one that is going to then dominate the flow of a current. So that is why we have 10 minus 0.7, that is now the V total. So 9.3 divided by the total resistance, which is 3k plus 4k. So as a result, we have 1.33 milliampere. And then just substitute that one in here, and then you will now get this value, which is 5.31 volts. Okay, so let me ask again, a random person. Sino pa bang di sumasagot? Mr. Bukat? Any question?
Wala po, sir.
Answer.
Okay, so if everything now is good, then I guess we can now proceed to the example number 5. So in here, solve for VO total current. So I think everything is the same. So in here, we just have a parallel connection of your two diodes. Okay, we have silicon diode and then silicon diode right here. So both of them have the voltage threshold of 0.7 volts. So here is the solution. So as you guys can see right here, we have 0.7 volts, okay, as your VO in here. So how did this happen? Because if you guys are going to take a look at this one, so in here, up to this point, we have this, we have this kind of flow of current. So some of the current will flow right here, and then some will flow right here. Okay. And then, of course, it will go back again to your voltage source. And then up to this point, we don't have a what do you call this one, a voltage drop or voltage across through this path. Okay, so that is why your only voltage reading is this 0.7 volts. Okay, because this path right here has a voltage wherein it's being powered by the silicon D2, which is 0.7 volts. So in other words, we have a closed loop, and then we just have a loop of voltage here. Okay, so whatever is the uh, diode in here, that is, or let's say if it's germanium, let's say 2 germanium, then the voltage reading on your VO is 0.3 volts. Okay. So that is why we have 0.7 volts here. And then for the I, of course, just get the total voltage and then the total resistance. So in here we have a total voltage of 7.3. Okay. So in here we've just assumed that it only passed through one. Okay, for now. Okay, so we can do that at one. And then in here we have 7.3 divided by 3K, you will get 2.43. But since we have two, okay, so all we need to do is divide this one current into two. Okay, since we have two the same silicon diode, wherein they will, the current will split equally. Okay, so 2.43 divided by 2 is 1.215 milliamp on each diode. And then for the R total, it's 3K ohms. Okay, so are we clear so far? Okay, so Mr. Muscat already got it. What about the others? Okay, Chris also got this one. Okay, so if you guys don't have a question, then let me the one to change the one diode. So let's say that this is not a silicon. Let's say this is a germanium. Okay, so and here we can apply what we have. Okay, as our past example a while ago. So if we have a germanium here, this will become 0.3 volts. Then this is now, or this one now has a lower voltage threshold. So in other words, all of our current will flow in here, and this one will become like an open circuit. So as a result, this is now the reading of our visible, which is 0.3 volts. Okay, and then of course you have to change this one wherein this will become 7.7 divided by 3K, and then that is now your answer in here. And then you don't need to divide it anymore, since this will break, or this will not work anymore as as a path, since this will become an open circuit. Okay, so I hope we're clear with that one, just in case that kind of situation happen. Okay, so we have example number 6 right here. So the question is almost the same. So solve for VO, total current, and then the total resistance. So we have two voltage sources. We have 12 volts and then 7 right here. But of course, you have to mind the polarity, because we have negative, positive right here. Excuse me, negative, positive, and then in here we have negative, positive also. Okay, or positive, negative, depending on how you read this one. Okay, so for the VO, you can solve it above or via below. So it should give you the same result. Okay, so in here we have 12 minus 0.3 minus the voltage drop across R1. Okay, so we cannot solve that one for now, since we don't have the total current. But yeah, it should give us the same result. So the same with this one. So we have so if we have positive, negative, positive, negative, we have positive, negative, positive, negative right here, and then positive, negative. So in here, if we are going to start below, since this is the voltage source, so we have a reading of -7. Okay, so I'm reading clockwise. So, and I'm also considering the outer part. So -7 minus negative this VR2 right here, and then minus this one, minus 0.7, and then it should give us the same result. Okay, so let's see how did that happen. So using Ohm's law, we have the upper part right here, wherein we have VO is equal to V1, okay, which is 1 minus VD1 minus VR1, okay, and just substitute everything, and then it will give us a result of 6.56. So the computed current is 2.57 milliamp. So how did we get this one? So you can use KVL. Okay, so just have a loop right here. So this one is connected to this point right here. Okay, so they are in closed circuit. So 12 minus 0.3 minus 2k times I minus 0.7 minus 5k times I minus -7. Okay, and then just simplify everything, and then you will get 2.57 milliamp. Okay, and then substitute it right here, and then this is the value you will get on the upper part. And then on the lower part, we have V2, okay, plus VR2 plus VT2. Okay, so as you guys can see, we now have plus in here, since in here we have negative, and then we have negative. Oops, this one is also negative, negative there. So negative times negative will become positive, and then negative times negative will become positive again. Okay. So that is why we have where is that one? -7 plus 2.7 milliamp times 5k plus 0.7 is equal to 6.55 volts. So they are almost the same. So maybe they just differs when it comes to decimals, but they are super close with each other. So the end of them will give you the same result, or correct the same answer. Okay. And for the current, so you can use Ohm's law. Okay, using this one, the total voltage divided by the total resistance, or you can use KVL. So it will give you the same value, which is 2.57 milliamp. And then for the R total, so just simply add this one, since this is a series connection. So 2k plus 5k is 7k ohms. So here so far.
Yes.
Okay, what about the others? Great. Okay, so if you guys don't have a question anymore, then let's now proceed to the last example. So solve for VO, same total current and then total resistance. So in here, we don't know where to start, but then again, we have to apply, the basics of electricity. So the one thing that we need to check is the voltage source. Okay, so whichever is the highest voltage source, that is the one that will dominate the flow of current of the entire circuit. Okay, so this one has 8 volts, and it has a voltage drop of 0.7. So this one is 7.3, and this one has 12, and then it has also a voltage drop of 0.7, so it will give us 11.3. And this one has 3, so kahit wag nyo na isolve to, alam nyo na wala ng pag-asa to. So in other words, this is where we are going to base the reading of your VO. Okay, so in here, we have VO is equal to V2 minus VD2, which is 12 minus 0.7, which is equal to 11.3 volts. Okay. And then I is equal to, of course, the total voltage divided by the R total. So V2 minus VD2 minus V3 divided by R will give you a result of 2.86 milliamps. And then R total is 5 kiloohms. Okay, so when it comes to getting the total current, so you also have to get the total voltage. So you have to consider everything. Okay. So are we clear so far? You're getting with this last example? So time check, I guess we now only have 50 seconds left. So that's pretty much it. Okay. So just in case that you guys have a question, okay, so just message me. So again, just a reminder, you guys have 2 quiz for this module 2, quiz on approximation and then quiz on diode circuit problem in series and parallel circuit. And then you guys also have to answer this case study number 2. Okay. And then just in case you need more information or you need more examples, then please visit these websites right here. Okay. And that's it. Yeah. So thank you guys for coming and see you guys next meeting.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you and goodbye.
Thank you po.
Thank you, sir.
Thank you too.